In the second part of this video on doing free fall problems, we will attempt to put down some important information for working problems and to at least start working on our first free fall problem. I remind you that from the first video that free fall problems are just a special case of constant acceleration problems where the kinematic equations are used. The only thing that's different about them than others is that we know the acceleration is 9.8 meters per second squared toward the Earth. So they don't have to give you the acceleration in the problem because you're supposed to know it. In other words, acceleration is g in whatever direction toward the Earth. So whether you have to put a plus or minus depends on your coordinate system. Let's write down some important other facts that we can learn and use in solving these type of problems. So here's some useful information in your notes. One of them is a lot of times you'll have a problem that's something like this. You have a ball, the ball is thrown upwards. Maybe I made this X, so this is, whoops, my fault. This is Y, so this is Vy naught. And it goes up here and eventually reaches some point where it reaches its maximum height. So as it goes up, it slows down because its acceleration is in the negative y direction, opposing the velocity, so it slows down until it reaches some maximum height. At that point, we know that the velocity upward is 0. So the vertical velocity of the object is 0 at an object's maximum height. So again, if they tell you something goes to its maximum, they do not necessarily have to say, and hey, by the way, know that the velocity is 0. You're supposed to know that. Another important thing, a lot of times you'll have problems, the ball goes up and then it comes down and it hits the ground. Well, you're not allowed to include hitting the ground. You have to stop the problem, if you're going to use the kinematic equations, to just before it hits the ground. Why? We said for it to be in free fall and to use these problems, we need constant acceleration. And in that, the only push or pull can be gravity attracting the ball toward the Earth. We cannot consider what's called the normal force, or the push or pull of the Earth pushing upwards, trying to stop the ball from going through it. So you may not allow it to touch the Earth. It has, likewise, if a person's throwing it, it can only be used, the free fall equations, after it left the person's hand. What the person's doing is giving it some initial velocity, but we have to consider have left the hand. It can be a billionth of a second after it left the hand, but it has to be after it left the hand. So the velocity is not 0 at the ground. Do not put that in. This is a common mistake students make. And last, sometimes you're lucky and the time a ball takes to rise is equal to the time it takes the ball to fall. And so people will do, they'll say, well, it took 2 seconds to go up, 2 seconds to go down, so total time it's in the air is 4 seconds. This is not necessarily true. Those are special cases. So be careful about that. Let me show you an example of one where it wouldn't be true. Johnny stands on a cliff like this, and he holds a ball out here, and he throws the ball upwards with some initial velocity. And I'm going to call that Vy naught because I'm going to make my coordinate axis so that y is pointing up. Now, the ball goes up, and I'm going to draw that separately out here. Goes up. I know it really goes up right there, but I'm going to do it just so you can see what I'm doing. And it takes some time to get there, that time being time t1. Maybe that's 2 seconds. After it gets up there, the ball then comes down, and the time it takes to come down to the same place it started is also t1 seconds. But that's not where it stops falling. It stops falling when it hits the ground over here. So the total time that it takes to get here, let's say, is t2. It fell from 0 to t2, so 4 seconds. Maybe it took 2 seconds to go up. The total time is 6. But the time it took to rise was 2. The time it took to fall was 4. They don't have to be the same amount of time unless the ball goes back to the same original height. By the way, if it goes back to the same original height, there's some other things that we can show with the kinematic equations. We can show that it will have the same initial speed. but its speed will now be minus because it'll be going in the opposite direction. Or if this was minus, this will be minus. A minus will be a plus. By the way, it isn't just initially. At any time, if you took a new position like right here, and you said that that speed was 1 meters per second, then when it comes back down, its speed will be 1 meter per second, but it'll be in the opposite direction. So the velocity will be minus 1 meter per second. So, would the final speed be the same as the initial speed if it goes all the way to the ground? No, by the time it gets down here, it will have fallen further, and it will be traveling faster than what you threw it up. These are things they don't tell you. These are things you're supposed to know or be able to find out. So, useful things, but we'll find out the kinematic equations will give us a lot of this stuff regardless. All right. Let's work a problem now. So here's a problem in your notes. A falling ball example. It's got two parts. I'm going to just do the first part A in this particular video. A flea can jump straight up to a height of 0.44 meters. What was its initial speed when it left the ground? I need a coordinate axis, so here's what I'm going to choose. Here's my flea. It has some initial speed in the y, vy naught. It goes to some final height where it's maximum. Its maximum point there would be y equals 0.44 meters. I get that right up here from the problem. Because I chose the way I did, this was 0 meters. Also, I know the speed here. Vy is 0 meters per second because it was at its maximum height. Now, if I look at this, this is a free fall problem. I'm going to write that down here among what is the physics? The physics is constant acceleration. And more precisely, free fall. And because it's constant acceleration, the kinematic equations are true. So these are equations that I think it might be useful to know. Y is y naught plus vy naught t plus 1/2 ayt squared. Do I have to write them down? No, I could do them in my head because I have a lot of experience. But you know what? When I do things in my head, I actually see these equations anyway. So I strongly suggest that you learn to write things down so that you can concentrate on solving the problem rather than remembering equations. And our last one, the final speed squared is the initial speed squared plus 2 times the acceleration times the displacement y minus y naught. Now, given. When you solve a physics problem, you want to write down givens. And the givens often come from the various statement of the question anyway, like numbers, heights, that's a good physics term, speed, all right, going upwards, tell me which way it goes. I don't care about jump and can and flee and so forth. Ground, I need to know where my original starting point are. And I write these things down. It could be mass, it could be more things as we go on. But when you're doing these kinematic type problems, it's always useful to write the little table that has everything. So my givens in this case are going to be a table. My initial position, my final position, my initial velocity, my final velocity, my acceleration, and my time. Those are the things that I can be asked. And if I've answered all of those, that's everything. This will be 0.44 meters. This is 0 meters. This I don't know. This is 0 meters per second. This is minus g, which is minus 9.8 meters per second squared. And the time I don't know. There's only two things I don't know. So no matter what type of problem I have, if I fill out this table, I've answered any type of question you can ever be asked about these kinematic problems. In part A, they asked me to find the initial speed. In part B, guess what? They're going to ask me something about time. Now, I'll go up and I'll simplify my equations to make them easier. Let's see, this is 0. This is 0. This is 0. This is 0. And in fact, I might rewrite these equations to make it a little easier. Y is vy naught t plus 1/2 ayt squared. 0 is vy naught plus AYT. 0 is Vy naught squared plus 2AY times Y. So those are my three equations, 1, 2, and 3. Three equations, but there are only two unknowns in the problem. That means that these equations overspecify. So there's actually probably more than one way to work a particular problem. In fact, I'll show you that in a minute. Now, I'm looking for Vy naught. So I'm going to look for an equation that has Vy naught in it. Well, all three of them do. So let's look at this equation. Do I know Y? Oh yeah, I do. It's right here, 0.44 meters. Do I know Vy naught? No. So that's one unknown. Do I know T? No. That's two unknowns. Do I know 1/2? Yes. AY? Yes. T. Two unknowns, one equation. You got to have at least two equations to solve two unknowns. On the second one, do I know Vy naught? No. Do I know AY? Yes. Do I know T? No. Two equations, two unknowns. You could work these two equations, substituting out T, and solve for Vy naught. Let's see if there's an easier way. Do I know Vy naught? No. Do I know 2? Yes. AY? Yes. Y? Yes. Just solve it. There's only one unknown. So if I do that, Vy naught is the square root of minus 2 AY times Y, and it's a plus or minus root. How do I know which one? It was initially going upward, so it's a plus to find the velocity. This is equal to the square root. AY is minus G. A minus and a minus makes a plus, so 2G times Y. Plugging our numbers in, Vy naught is the square root of 2 times 9.8 meters per second squared times 0.44 meters. 2 times 0.44, that's around 0.88, near 9. This is near 10, about square root of 9, therefore. So 2 times 0.44 times that's about 9 altogether. Square root of 9 is about 3. Plug in your numbers, and what you'll find out is it happens to be 2.94 meters per second. Notice, meters squared takes square roots of meters. Square root of second squared is a second. Therefore, this makes sense. The units check out, the numbers check out. Practice learning to work in symbols. For instance, back up here in this formula, had we doubled the velocity, 2 squared would be 4. We would make the distance or the height the object could go 4 times larger, not twice. You can't get those type of understandings if you plug in numbers. I also can see what can happen if you make gravity. If you make gravity equal to 1/6, you get the square root 1 over the square root of 6, which is about less than 3, more than 2. You need less velocity in order to get the same height on the moon. In the real world, when you're solving for an airplane wing, when you're designing something, when you're a physicist who's out there trying to discover new laws, you don't have numbers. If all you can do is punch numbers in, you're going to limit your job opportunities, and you're going to limit how much you can make. Because after all, I can get the numbers from instruments and directly put them in to the computer, then I don't need you anymore. But the person who can work and ask what if, what can happen, who can work with algebra, they're the person who can make the bigger money. They're the person who can go to med school and law school, who can become a physicist, be an engineer. So make sure you're practicing in a way that takes advantage and builds the skills you need for the future, not just get by. Because getting by won't help in the long term. All right, in the next video, we'll do the second part of this problem.